4-8, complex numbers. So in this section, our objectives are to identify, graph, and perform operations with complex numbers, and to find complex number solutions of quadratic equations. And what we have to realize is that complex numbers are based on a number whose square is -1. And if we try to think about this, two numbers that multiply together to give me -1, well, 1 times 1 is 1, and -1 times -1 is also 1. So I can't really think of any number that if I square it, if I multiply it by itself, that is going to give me a -1. So this number does not really exist in our real number system. That's why we have a special type classification for it called a complex number. So what we're going to do here is in chapter 1, we learned all about the subsets of all the real numbers, which are right here: rational numbers, integers, whole numbers, natural numbers, and irrational numbers. So all these numbers are considered real numbers. Okay? Now, what we're going to say today is that this set of real numbers is part of a much larger set of numbers called the complex numbers. Okay? And this is only a small section of the complex numbers. And the numbers that we're going to talk about today are going to exist, in the rest of this section. Okay? And I didn't show you the solve it, but there's a unique thing with numbers that its fifth power is itself, which is going to act like our imaginary unit, who we name I. Okay, so the imaginary unit I is a complex number whose square is -1. So I squared is going to equal -1, which means that I is going to be equal to the square root of -1. Well, you're probably thinking, but it's a negative underneath the square root. I'm not allowed to do that. True, in the real number system you are not, which is why we are not inside the real numbers anymore. We're talking about numbers that are outside the real numbers. Okay? So we know that I is going to be equal to the square root of -1. It's an imaginary number, imaginary unit. With this, I can now take square roots of negative numbers, which means that if I want to take the square root of -a, I can separate that into the square root of 1 times positive a, separate that into the square root of -1 times the square root of a, and I know that the square root of -1 is equal to I. So my answer will be I times the square root of a. Seen right here, where the square root of -5 is equal to I times the square root of -5. And note that when we square i's, we get negative numbers, not positive numbers. And we'll get more to this later. Okay? But first, let's simplify the square root of 18 with the imaginary unit I. Okay? So first, I'm going to take the square root of 18, and I'm going to separate it into the square root of 1 times the square root of 18. And I know that the square root of 1 is, write that better, I. Okay? Can't leave it like that, though. It's not finished. Okay? We need to simplify the square root of 18 as well. So I have I times the square root of 9 times the square root of 2. And the square root of 9 is just 3. So we have 3i square root of 2. Okay? Just a little note on notation. I like to put the I right there, because if we do it the other way, if we do 3 square root of 2, 3 square root of 2i, it becomes hard to tell if the I is underneath the radical. So it is best to leave it in front of the radical, in between the 3 and the radical 2. Okay? Next, we're going to talk about that I is my imaginary unit. Okay, now, an imaginary number is any number that has the form a plus bi, where a and b are both real numbers and b is not 0, or else I wouldn't have an imaginary unit anymore. Okay? And real imaginary numbers and real numbers together make up the set called complex numbers. Okay, so my imaginary number is going to be some number plus a number times the imaginary unit I. Okay, and if we look at the chart of this, when we look at the chart of complex numbers, we can write complex numbers in the form of a plus bi, where a and b are both real numbers. Okay, that means that any complex number, any real number, can be written like this. It just doesn't have any imaginary parts. So if I think about a real number, say 2, well, that can be written as a complex number, 2 plus 0i. And the 0i would just go away, which gives me my real number of 2. Now, imaginary numbers are numbers that do have an imaginary part, a plus bi. Okay? And a pure imaginary number is something with just the imaginary part. So, for instance, 3 plus 2i would be an imaginary number, and 5i would be a pure imaginary number because it doesn't have a real part associated with it. Okay? Because a would be equal to 0. Now, all of these together, the real numbers, the imaginary numbers, are all part of a set called the complex numbers. Okay? So try not to get confused about that. Okay? So, when we want to graph complex numbers, we have to graph it in the complex number plane. And the point AB represents the complex number a plus bi. And if you think about this, this is going to be the real axis. Think of that as your number line, your standard number line, which would look like this. Okay? If I wanted to graph, negative. If I wanted to graph 1 on the real number line, I would put a dot right there. But what if it's a complex number? What if it has an imaginary part? Then I would lift it off the line, and it would go up or down depending if it was positive or negative imaginary units. Okay, so look up here on the graph, and we can see that this is the graph of 3 minus 2i. So I would go in green, I went right 3, and I stopped right there, and then I went down 2i. And we have my point, which would be right there. That would be 3 minus 2i. Okay? Real parts are on the horizontal, imaginary parts are on the vertical. And then the absolute value would be its distance from 0. So in order to do that, I just use the distance formula, which is going to be whatever number's here, a squared plus b squared, because those are both distances. Distance from 0 is 3. Distance away from the line is 2. It's 2i, but it's 2 spaces. Okay? And then we just add them together and take the square root to find the distance. Okay? So, graphing 5 plus 3i. So what are the graphs in the absolute value of both numbers? So let's do both of them together. 5 plus 3i, or sorry, negative 5 plus 3i would be minus 5. 1, 2, 3, 4, 5. 1, 2, 3 would be right there. And its distance, okay, would be the absolute value of negative 5 plus 3i would be equal to the square root of negative 5 squared plus 3 squared, which would be 25 plus 9, which would be the square root of 34. Okay, which doesn't really simplify at all. Okay, and now this one, a pure imaginary number, okay, would just be 6i. So that's 0 left and right and just 6 up. And its distance, because it doesn't go left and right at all, is just going to be 6. And we can see that because the absolute value of 6i would be equal to its real part, which is 0, plus its imaginary part, which is 6. So that would be the square root of 36, which is 6. So graphing an absolute value shouldn't be too difficult. Okay? So now, let's talk about addition and subtraction, multiplication and division. Okay? We can define operations on the set of complex numbers so that when you restrict the operations to the subset of real numbers, you get familiar operations on the real numbers. So what does that mean? That means that our complex numbers are going to act like real numbers, and everything that you do is going to be similar. Okay? When we add and subtract, we're going to put the real numbers together. When we add and subtract, we're going to put the imaginary parts together. We're going to put the different parts with their same parts. Just like when you add x and 2x, right? You add it together, you get 3x because they're like terms. They go together. Okay? So to add or subtract complex numbers, combine the real parts and the imaginary parts separately. If the sum of two complex numbers is 0, or 0 plus 0i, then each number is the opposite or additive inverse of the other. The associative and commutative properties apply to complex numbers as well. So all the rules of addition and subtraction, multiplication and division that we know how to use apply to these numbers as well. Just got to be careful because they're going to have an I in it. But if you think about it as almost like a variable, combine the real parts and the imaginary parts separately, we can see that this is going to be pretty easy. 4 and negative 4, 0, negative 3, positive 3, plus 0i. That means that this is going to be equal to 0, and it means that they are additive inverses of each other. Okay. For part B, don't forget that when we subtract, let's do this, 5 minus 3i, when we subtract parentheses, you must distribute the negative. So that turns into plus 2 minus 4i. Putting the real parts together, 7. Put the imaginary parts together, minus 7i. Okay? So there's no real difference here. All we're going to be doing is adding real parts and adding imaginary parts and combining them with their like terms. Okay? Now, when we multiply complex numbers, like a plus bi and c plus di, when we multiply them, we're going to multiply just like we do binomials. This means that because they're binomials, I'm going to have to FOIL them together. Okay? Now, for the imaginary parts, bi and di, this last term, when I multiply those, I get bd I squared. But I know that I squared is going to be equal to negative 1, which means that bd changes sign to negative bd. Okay? Everything else is going to act the same, except that when you get I squared, it's going to be equal to negative 1. Okay? So let's see how this works. First, get to that in a second. What's the product? The rules of multiplication don't change. We have to distribute the negative 3i. So let's do it there first. 3i times negative 5 is minus 15i. 3i times 2i is plus 6i squared. But the 6i squared changes into negative 15i plus 6 times negative 1, because I squared is the same as negative 1, which means this becomes 15i minus 6. But I don't want to leave it that way. I want to write it with the real part first and then the imaginary part. So write this as 6 minus negative 6 minus 15i. Okay. Let's look at this one. Ooh, whoops. Let's look at this one next. Okay. Now, we are going to have to FOIL these two terms. So, first, negative 4. Outside, minus 8i. Inside, minus 3i. And the last is going to be minus 6i squared. I squared is going to change into minus 6 times negative 1, which is going to turn this into a plus 6. And then I'm also going to combine these two because they're like terms. They both have an I. That's going to be negative 11i. bring that down over here. And then a negative 4 in the front. And then finally, those two can combine to give me 2 minus 11i. Okay. Just important to realize that the last terms, when I multiply the last terms, 3 times the 3 and then negative 2i, right? And I get I squared, I have to remember to change it to negative 1. Now, sometimes something special can happen. As we're looking at this, I notice that the real parts are the same and the imaginary parts, the imaginary parts are opposite. I have plus I, I have minus I. Let's see what happens. Negative 6 times negative 6 is positive 36. Outside, negative 6 times negative I, that's plus 6i. Inside, minus 6i. And the last would be negative minus I squared, which changes into negative 1, which changes into plus 1. Minus a minus 1 turns into plus 1. And look here, we have plus 6i and minus 6i, so they cancel each other out. So my answer is 37. So what just happened is that I multiplied two imaginary numbers together and I got a real number out of it. That is very important. Okay? And it shows me that I have something called complex conjugates. So in problem 4c, the product is a real number, 37. Number pairs of the form a plus bi and a minus bi are called complex conjugates. The product of complex conjugates is a real number. Okay? Any complex conjugates, because it's always going to give me, the middle terms are always going to cancel out, and the last term is going to be minus bi squared, which is always going to turn into plus b squared. So if I have a pair of complex conjugates, my shortcut to multiply these together would just be to take the first number plus the second number squared. Okay? And we can use these to simplify quotients of complex numbers. Because just like you are not allowed to leave a radical in the denominator, we are not allowed to leave an imaginary number in the denominator. So we are going to use complex conjugates to help me clear them. For instance, this problem. Okay? So what I can do here is I can multiply the top and the bottom by the conjugate of 3i. Now that's a pure imaginary number, so the real part doesn't change. Notice back here, the real part doesn't change, only the imaginary part changes signs. So this would be, the conjugate would be negative 3i. Okay? Multiplying these two together, let's start with the denominator. This would give me negative 9i squared, which would turn into a positive 9. Okay. Next, 9 times negative 3i would give me a minus 27i, and a 12i times a negative 3 would give me a negative 36i squared, which would change to a positive 36. And of course, I can write this as 2, the real part, and the imaginary part. But, of course, you should recognize that this can be reduced to 4 minus 3i. Let's rationalize this one. Multiply by the conjugate of the denominator, not forgetting to substitute negative 1 for I squared. The conjugate of the denominator would be 1 plus 4i. And of course, I have to multiply the top and the bottom by 1 plus 4i. Okay. Let's do the denominator first. Okay, let me use my shortcut that I know that when I multiply these two things together, I'm going to get two conjugates together. I'm going to get a squared plus b squared. Okay? You could FOIL this whole thing out, but I just know that it's going to be 1 squared plus 4 squared, which is 16. So the denominator is going to be 17. Okay? No shortcut for the top. I'm going to have to FOIL it out. 2 times 1 is 2. Plus 8i plus 3i. And then the last terms is going to be plus 12i squared, which turns into a negative 12. Okay? Combining the real part and the imaginary part, I get negative 10 plus 11i, both over 17, which does not simplify at all. Okay? So we can use this idea to also help me factor. Okay? First, before we even start to factor this, I should realize that I can factor out a 2 to give me x squared plus 16. Now, that is the sum of squares. The sum of squares factors kind of like the difference of squares. The difference of squares, if you remember, whoops, a squared minus b squared factors into a minus b times a plus b. So if this problem said x squared minus 16, it would factor into x minus 4, x plus 4. But it doesn't say x minus 16. It says x plus 16. So when I have the sum of squares, I can factor it using the properties of I. So this would factor into x plus 4i and x minus 4i. Because when I multiply two conjugates together, two complex conjugates together like this, I get the sum of squares, like we saw a few pages back. Okay? So when we have the sum of squares, you can factor it using complex conjugates. Now, putting this all together is every quadratic equation has complex number solutions. In fact, it always has two complex number solutions. Sometimes they are real, sometimes they are not. So, sometimes they're not real solutions, like they're going to be here. But let's see. First, looking at that, can I factor it? No, there's no factors of 2 times factors of 5. That add up to 3. Okay? Next, can I complete the square? No, because I can't get rid of that 2 without giving me fractions. Okay? So my only other choice to solve this is going to be the quadratic formula. Negative b, that x is going to be equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. Okay? And a is going to be equal to 2, b is going to be equal to negative 3, and c is going to be equal to 5. Okay? So, plugging these numbers in, we have that x is going to be equal to 3, negative 3, plus or minus the square root of 9 minus 4 times 2 times 5 all over 4. Okay. Next, we have 3 plus or minus the square root of 9 times 40. Or sorry, 9 minus 40 over 4. Well, that's 3 plus or minus the square root of negative 31. But there is no square root of negative 31. So that means that I have to change this radical into an imaginary unit. Okay? So my answers become x is going to be equal to 3 plus or minus I times the square root of 31. The negative can come out by becoming an I, which is what I wanted to do, over 4, which makes my two answers, x is equal to 3 over 4 plus or minus the square root of 31 over 4i. Okay? And that is now, first of all, the determinant, the number underneath the radical was negative, which means that there were no real solutions, but I still get two solutions. They just happen not to be real. They happen to be imaginary numbers, which also means that this graph does not cross the x-axis at all. It opens up because of the 2, and I could figure out the vertex if I really wanted to using negative b over 2a. But the important point that we're getting here is these are the two solutions to this quadratic, even though it never crosses the x-axis. Okay? And that is 4-8 complex numbers.